So how many of you have heard of Duolingo? Geez, everyone, I think. Maybe one or two people. How many of you use it? Okay, so about half that. So for those of you who don't know, this is our mission statement: free and accessible language education for all. And this kind of defines everything that we do. You have the most downloaded education app in the world, both on iOS and Android. We're in every major country in the world. We have 30 languages that you could learn across 80 different courses. Anyone want to take a guess on what our most popular language to learn is? English, yes. There is an enormous demand to learn English, especially in developing countries. It allows for great upward mobility from poverty. And we really think about this. This is one of the main things that we do. So we found that Duolingo is actually not only fun, but fairly effective. So we did an independent study a few years ago with a major university, which found that 34 hours on Duolingo is roughly equal to one university semester of Spanish. So it's quite effective. Right now, we have over 300 million users. This is actually about a year out of date, so we have more than that now. And we support that many users with only about 180 employees. This is also a little out of date. We're closer to 200 now, less than half of which are engineers. So this is a graph of our user growth compared to the number of employees. So this is a little crazy for even me to think about, since I've been with the company for about 5.5 years, and I just constant growth. Like, it never slows down. There's always new challenges. So we have over 1 million users per employee. It's a little crazy to think about. So a brief history of our infrastructure. So we launched in late 2012. We were born on AWS, or Amazon Web Services, which is infrastructure as a service. This is our original logo. I actually still kind of like it. It's kind of cool. It was a Python 2 stack, and all of the infrastructure was manually built. We had some very early bash scripts, a little bit of Chef, but most of it was completely hand-built. There weren't too many AWS services back then. There was like S3, EC2. So S3 is like an object store. EC2, you could think of it as a virtual machine service. And RDS, which is a database service. So MySQL was pretty much the only option, I believe, back then. NoSQL databases like DynamoDB did not yet exist. So this was just Python with an RDS backend. I think we might have had a cache or two. This is before my time. But yeah, monolithic, manual deployments, manual everything. So I joined around 2014. One of my first tasks was to get config management into the company. We ended up deciding on Ansible. I was familiar with Puppet, but Ansible was definitely coming into the fray. I'm really glad that we use Ansible, because that has essentially become the de facto standard now. Sorry if you use Puppet, but I don't know. I feel like Ansible's kind of won. So at this point, everything was in Ansible, and we're actually able to have an automated process to build machine images, which was a great starting point in terms of automation. So another year or so passed, and again, we had this monolithic Python application, and I was responsible for dozens of deployments per day. We were a very quickly moving company at the time, which I'll discuss a little bit more. We weren't auto-scaling, so we would just add machines when we needed them. And around this time, we started auto-scaling, which was actually a pretty big challenge back then. It seems like old hat now, but it was a pretty big deal, and we actually saved a significant amount of money by doing so. And then we also started to think about microservices. So we had a newly formed architecture team that tried to come up with service templates for our engineers so that they could start with this baseline and then build from there these new microservices. And we originally ran them on Beanstalk. And the reason for that is just so that a team could fully own the stack. It was fairly easy. We eventually got rid of it, which I'll discuss. But at the time, it was the correct decision. And then we started to centralize a lot of the view into the infrastructure and also handing things off to the teams. So we put an elk stack in place so you could view all the logs and search them. So the teams can manage their own services and keep track of them, so it's not just me and one other person on the ops team. We also started to create standardized dashboards and allow teams to create their own dashboards, their own views of the things that they care about in their service. Grafana was one of the life-changing things, so if you haven't checked out Grafana, definitely do that. And then shortly after that, we started to look at Terraform. So I had an intern, and his job was to import all of our existing manually built infrastructure into Terraform, and then at least we had a central repository where we can make changes. Again, that was definitely life-changing as well. And then we started to get really serious about microservices. Beanstalk was just not scaling. If you know anything about Beanstalk, when you use it with Terraform, it doesn't really jive very well. Beanstalk is very monolithic, and you end up with thousands upon thousands of configuration parameters, and it just becomes a huge mess. So what we ended up doing was building an entire new infrastructure platform based on ECS, which is AWS's proprietary Elastic Container Service. Kind of similar to Kubernetes, but a lot less complex, and they manage the whole thing. So let's jump back. So why move to microservice at all? I mean, we had a monolith. It was okay. It was running. But the thing is, at a certain point, when you have enough people, again, you're going to run out of time in which to do deployments for all the teams on a given day or a given week, depending on your deployment strategy. So we not only wanted to scale the application horizontally, we also wanted to scale the team. So the teams themselves. So we didn't want to hire, one or two ops people or one or two engineers for every single service that we had, right? So we're going to make these applications small so that maybe one person can manage 2, 3, 4 different services. Velocity, again, most of this relates to deployments. So when you have microservices, all the teams can independently deploy. You're not stuck with a centralized team. Flexibility, we started on Python 2, but engineers wanted to run Node.js. Python 3 was coming into play. Java, people wanted a more enterprise-y language. Scala was a big deal at the time. And then reliability. Up to this point, we had never hit 4 nines and a quarter, and that was becoming a really big goal for us. And with a microservice architecture, you could put in things like circuit breakers, which will cut off access to poorly performing or services that are down and keep the rest of the infrastructure up. And also cost savings. A few years ago, our AWS costs were steadily increasing with the number of users, and it was becoming really significant. Any of you who are on AWS know that there are lots of hidden costs and things to worry about on those platforms. So we had to decide what to carve out of the monolith. So this is what I would recommend. So start with something small but impactful. Don't try to carve out the largest piece, because you'll probably never, ever finish, and it'll just become a nightmare. And then move up in size, complexity, and risk. So we found with every single piece that we carved out, or microservices that we had moved from Beanstalk to the new ECS framework, there was a problem every single time. It was amazing. I thought this one's going to go smooth this time, and every single time we hit this huge roadblock, brand new problem. It was quite the process. But by the very end, things were really smooth, and now we can onboard microservices in a few hours, where it used to take weeks. So the first thing we carved out was a reminder service. This is just a service that reminds you to do your daily lesson, just sends out an email or a text message. And that was actually really impactful. Our daily usage is actually highly impacted by these reminders. And you also need to consider dependencies. So let's just look at some raw statistics. Let's say your monolith uptime is 2 nines. Not great, not terrible, right? But you split that into 3 different services that have the same uptime, and suddenly you're at 0.97, which is worse. Because if they're all tied together, they're all going to go down if one of them goes down. But if you make them independent, you're now at 6 nines of uptime. So this is the ultimate goal. And you can achieve that with circuit breaking libraries. There's a few out there. Netflix has one. We ended up building our own circuit breaking library for Python internally. But this is where you want to get. You don't want to chain things forever. And especially, you don't want to have all the dependencies still on the monolith while you have microservices. Or worse yet, have a circular dependency between the monolith and a microservice. You just made everything much, much worse in terms of uptime. And Netflix's tool is called Hystrix. So why use Docker? So I'm not the biggest fan of Docker. It took me a long time to get used to it and actually use it. But it's one. You kind of have to use it if you want to do containers. The main advantage is that it standardizes the build process and encapsulates dependencies. So you move from these weird scripts for every service or team to this nice standardized Docker file. And it allows for very quick deployments and rollbacks. So rather than it taking minutes, many minutes if you're on like a physical server, to boot up and start the application, it might take seconds. So if you have a failure and your service crashes, it can very quickly come back up. It also allows for flexible resource allocation. So when you're on these cloud platforms, generally you have a fixed size of CPU and memory, but with Docker, you can kind of have an infinite size and scale. So you could actually scale the memory and CPU to the application and not the other way around, which is quite nice. So in terms of simplifying local development, this was how we used to do things. This was like a long step of manual tasks that you had to run in order to get this service to work locally. Please don't screenshot this. It's not relevant at all. So we went from this to this. And actually, we've gone a step further now. We have a script that does both of these for you. It's like run.sh. So that's great. So every new employee that comes in, every service is coded in such a way that you could just do build and up, and it'll start in your local machine. You could get started very, very quickly. So let's go back to ECS. Why did we choose ECS? So this was almost a little over 3 years ago when we were making this decision. Kubernetes was out, but it still seemed extremely scary to me. There was a 1,000 node limit, and we were nearing that on EC2, so I was like, I don't know if that's going to work. Also, ingress was a problem back then. I think most of these things have been solved. And there was also HashiCorp Nomad, which I like a lot. It fits very well into the Terraform system. But we went with ECS. So it provided a lot of really nice features that the others didn't. So we had task-based autoscaling. A task in this instance is just a group of containers that kind of work together. So you might have a service and then a logging daemon, and they're grouped as a task. You might have lots of different what are called sidecar containers, where it's not the actual application, it's just something that kind of helps the service along or monitors the service. We had auto-scaling for this, so we didn't have to have a fixed number of containers. They would just scale with the amount of CPU or requests. Very easy. And also something that we were used to at the time. We also had task-level IAM. So IAM is the way to give permission to the service so they can access some other AWS resource. And with this, we could actually do it at per service level. Even if there were different services running on the same machine, they would all have different permissions, so that you would have some really nice isolation there. You wouldn't have to assign all the permissions to all the machines in the cluster is very nice. And also teams could then manage their own permissions, which was a side benefit. We use CloudWatch. So CloudWatch is Amazon's monitoring service. So all the metrics coming from all the other AWS services. ECS fits very nicely into that. And then the load balancer. So ALB stands for application load balancer. So it's layer 7 load balancer. And if you've ever worked with Docker, you know you're normally dealing with ephemeral ports. And this nicely maps to some external port for you automatically. And then manageability. At the time, we had an ops team the size of 2. We're now at 5. And we just didn't want to manage, you know, a Kubernetes cluster or a Nomad cluster. We just wanted it to work. So using Terraform, we created a bunch of abstractions for our teams using Terraform modules. And you could think of a module as a library for Terraform code. So we created 2 services, a web service, might be internal or external, to the world, or a worker service, which could be daemonized and feed in messages from a queue, or it could be cron-based, time-based tasks. We also had a bunch of different data stores, so we were using our relational database service, so Postgres, MySQL, KMS allowed us to encrypt passwords and keys, and then we had res and memcache caches, and also NoSQL DynamoDB, which we were one of the largest users a few years ago. I'm sure someone has surpassed us, but we also had monitoring. So all these things were now starting to tie together. So we didn't really get rid of the old infrastructure, we just built upon it. And we have now CloudWatch talked in Grafana, and the Elk stack, you could view logs within Grafana, and then this was all tied into PagerDuty, so you can get alerts if something went above a certain threshold. And then we were also feeding all of our alerts to Slack. We're huge users of Slack. I swear I get like 2 internal emails every couple days. Everything is on Slack, for better or for worse. And for the web service, you could also put some other things in front of the load balancer, like a web application firewall or a WAF, or even a CDN, like CloudFront. It's very modular. So this is the engineer's view into their service at a high level. So these are the only parameters they have to fill in. Everything else is done for them with Terraform. So let's just quickly go through here. Like I said, billing is very important when you're at a certain scale. So these are all mandatory tags. So what sort of environment are you in your production staging? Dev, product. So this, for instance, is our main Duolingo API, which the app or the web service interfaces with. And then an owner. So you have to know who to talk to if you see a bill going completely out of control for a particular service. And then we have the min and max count. So this is how we tie into auto scaling. This will scale based on CPU. The amount of CPU and memory allocated to each task. And here is a database. So this is Aurora. This is kind of Amazon's equivalent of Oracle, our competitor now. This is a Postgres database. Again, billing tags. You can see that we now have a subservice of DB as opposed to API. Aurora Postgres is the database engine. We also allow MySQL. And then this is the instance class. So if you're not familiar with cloud services, I'm going to be using this a lot throughout the rest of the talk, so I guess I'll kind of explain it. So R4 is a family, so it's a family of a type of machine, and this is a memory based instance. So it has a lot more memory than it does CPU, and then the size. So that's basically the amount of CPU and memory that it has. So this is our continuous integration deployment cycle, CI/CD. We use Jenkins for our builds and deployments. We build a Docker file after doing a whole code review process in GitHub, and then we push it to an Elastic container repository. So that's kind of a Docker Hub thing that Amazon manages for us. And then we do a plan and apply with Terraform to actually do the deployment. So we feed in a version number, and that forces a brand new version onto ECS. And I should mention that ECS functions as a state machine. So if you feed it all the same information in, it's not going to change anything. You have to keep feeding a new version number in if you want things to redeploy. Okay. Oh, I should also mention, I don't have it up here. We use this great tool called Atlantis to actually code review our Terraform code. What that does is it runs a Terraform plan and puts the output on the GitHub PR, and then you can run your plan apply actually through GitHub. It's really fantastic. Let's talk about load balancing a little bit. So when we were doing this transition from EC2 and Beanstalk to this new containerized environment, we were using ELBs, or what are called elastic load balancers. It was the first iteration of load balancer on AWS. They have now confusingly renamed them to CLBs, or classic load balancer. So I'll just refer to them as CLBs now. But ELB is still spread throughout all the APIs. It's a horrible mess. It's very confusing. But yeah, we were moving to CLB/ELB to ALB, which is an application load balancer. It actually works with Docker and ECS really well. The problem is the ELB was a layer 4 load balancer, so if you had TCP applications, you could not port those to the ALB, with the ALB being a layer 7. And the ALB also suddenly started to support HTTP2. And if you've ever worked with that protocol, you know that there are actually quite a few differences between that and HTTP. One thing we ran into very quickly was that headers are always passed as lowercase. We actually had some services that assumed they were always uppercase, which was kind of funny. And then ALBs are also a lot more strict. They're dealing with a higher layer, so they were not taking the malformed HTTP requests. We were getting all sorts of weird error messages. It was really, really hard to debug. And this was because our applications were creating custom requests to the load balancers. Like I said, every single new service ran into something strange that we hadn't before. There are also differences in how Amazon presented the metrics. So the ELB provided very nice, smooth, connected dots. And suddenly with ALBs, probably to save space on their back end, if there was a request, they just like throw a dot down. And if there were 2 requests within like 1 minute of each other, they would connect them. So we'd have these like weird things. So we had to figure out how to actually connect the dots in the graph so they wouldn't look really strange. Yeah, let's go back to task level IAM role permissions, because I find this is really important if you care about security and isolation between your services. Again, they apply service permissions at the task level, or in our case, service level. Really do not share permissions and policies across services, because what can happen with Terraform? All sorts of badness. You might write some Terraform code that might blow away a completely different service if you're not careful. If they have the same state file, or you accidentally forget to change the state file path, you might blow away a service. So we try to keep all the policies completely independent. We try to keep all the resources for every service independent so they don't share resources, just in case something bad like that would happen. The catch is they need to be, the task level permissions need to be supported by the client library that you're using. So there are 2 client libraries for Python. One is Boto 2, which is the older version, which doesn't support task level IAM role permissions. We're actually still phasing this out for some of our services. But Boto 3 does, and that's the one that you want to use from here on out, because they're actually making changes to that service now, or to that client library. The other important thing is standardizing the microservices, how you create them, how you name them. You should be establishing this day one. I can't even imagine running half a dozen services without some sort of standardization. So again, develop a common naming scheme. auto-generate as much of the initial code as you possibly can just to make it easy to onboard new services. Move core functionality to shared libraries, especially any interactions with AWS, because you're likely going to be doing that a lot. You want to keep that functionality very clean and share it so that not every service has to re-implement that sort of functionality. Also, we're very big into providing standard alarms and dashboards. So as of probably a little over 6 months ago now, every single engineer in the company is on call. So what does that mean? You're going to be on call for services you may not know very much about. So it helps to have the same dashboards for every service. We allow teams to create their own front-end custom dashboards if they want, but they also have these automatically created dashboards behind that just to provide a nice, stable interface. We also periodically review microservices for consistency and quality. So people might rotate in and out of teams. They may have a varying understanding of how the service actually works when they're making changes, so the code can get kind of crufty. So you have to kind of reel those services back every once in a while. So this is what one of our standard dashboards for a web service looks like. So an important thing is we have both local time and UTC at the top. For whatever reason, when you're looking at the Amazon web interface, some metrics and screens are in local time, some are in UTC. It drives me insane. It just kind of demonstrates the silos within Amazon. So sometimes you need both. All of our internal timestamps are UTC, but for whatever reason, there might be something weird they're looking at where it's not. So I think it's really important to have that. We also show healthy, unhealthy containers and the number of running tasks for each service, latencies, number of requests, CPU. And another important thing is to split all the errors by both load balancer, which will show all the errors in front of the load balancer might be handling, that may never get to the service, and then also show the service errors. And we also split this by AZ. So if you're not familiar with the terminology, that's an availability zone, which is kind of one or more physical buildings within an Amazon region. So you could just kind of think of that as one or more data centers. And they're supposed to be completely isolated. That's not always true, but it's still a good thing to see because one of those buildings might completely lose power. So if you see one AZ across all your services is throwing errors, you might just knock that AZ out and scale up across other AZs. We have a worker dashboard here, which is very similar. It's much more simple, obviously, because you don't have requests and those sorts of things. CPU and memory. We also have a queue, which shows the number of messages available and the number of messages deleted. So if the number of visible or available messages keeps going up and up and up, you know that your worker service is struggling. And we also integrate this all with PagerDuty and define all of our alarms within Terraform itself. So we have a bunch of default alarms, but the teams are very welcome to adjust those as needed. We also have a high latency, an emergency alarm, which will actually page, and then an example of a low alarm would be memory usage. If we get to 100% and tasks start shutting down, that's a problem. But if we get to like a 70 or 80% memory, it's normally not a big deal. It can wait till the next morning. And another important thing is to have playbooks. Again, if a lot of your engineers are on call with services they're not that familiar with, include links in the alarm so they can just click through. Nice and easy. I talked about grading of microservices a little bit. So we gamify learning. We try to gamify this process to kind of make it fun. So we have 4 different levels. So bronze, silver, gold, and platinum. So if you have a service that has all platinum shields, that's like top of the top service. You want to get there. And we have all these different categories. This is what one of our grading rubrics looks like. So the The green checks are actually automated, so we can do a lot of checks on each repo automatically. I should mention every microservice has its own repo, and within each one of those repos we have different Terraform environments. So all the Terraform code for each service lives in its service's repo. That's really important, I feel. So we have some automated checks. So like, is there a README file? And then we have some things that you can't really check automatically, like, is this good code? You know, what we do is we kind of sit in a conference room and just, you know, take a look and see, oh, that doesn't look so great. I don't know. That's a bronze, something like that. Now, if you have a way to automate that, please let me know. I'd really like, you know, automated code quality checking. Okay, so now we're going to talk about cost reduction. I love reducing cost in infrastructure. It's really fun, for me at least. So when you're in a Dockerized environment, there's normally two ways you can reduce costs. So you can reduce the cluster. So this is the large group of machines where your containers actually run. So you could have different instance types. So these are the sizes of VMs available from Amazon. You could have different pricing options. Oh boy, there's so many options in Amazon. You could have, you can pay for machines up front, which gives you about 40% cost reduction. You can do them on demand, where you have 100% of the cost that you pay incrementally per hour. There are also things called spot, where you actually throw in bids, where you can get up to 90% cost reduction, which is nice. But the catch there is the machines can disappear within 2 minutes at any point in time. And I'll get into that. You could auto scale. So if you're just running, you know, the same number of machines at all times, and your traffic looks like a sine wave, well, you're probably wasting a lot of money. So you want to auto scale, but there's also, you know, dangers with that too. So you have to weigh stability with cost. And you could also add or remove AZs. And you're probably like, this is weird. So like, what does it matter whether we add more data center buildings or not? Well, the reality is not all the data centers have the same physical machine types. Or one data center might have really old servers and one might have fully new servers. They're much faster. And Amazon doesn't really tell you this, but it's totally true. All the data centers in each region are not equal by any stretch of the imagination. Because they'll fill up like an entire building and then build a whole new building, and those will have all new servers. I mean, it totally makes sense. So the other way to save cost is by actually tweaking the tasks of the services themselves. So, you know, not using too much CPU or memory. And you could also auto-scale the tasks. So the containers within the machines themselves. So back when we first started and launched this in production, this is now 3 years ago, we started with this fixed machine type. We were actually using this for almost everything at the time. It was probably 70% of our infrastructure. So a C3 family, so it's compute optimized rather than memory optimized with a size of 2x large. I believe that was 16 gigabytes of memory. Please correct me if I'm wrong, but I think that's what it was. And we bought some reserve, so that means that we paid up front for a lot of our machines. And then the rest was on demand. So we got roughly a 4% cost savings on maybe 40 to 50% of our infrastructure at the time. So fast forward a year or two, the C4 large came out. The problem there is it didn't have a local disk. It just had a network-based disk option, and we were doing a ton of logging, and that would have cost a ton of money. So we actually skipped that. And then one of the best days of my career was C5D came out, which local NVMe storage, that was really great, which was also 25% faster than the previous generation, and also cheaper. So it was 9 cents per hour. And if you do the math there, the C5 was also 50% faster than what we were using. So win-win, really great. The problem is, keep going, is how ECS was actually scaling the tasks, which was really weird if you think about it. So they had this CPU unit, which just counts the fractions of a core. And if you think about it, like cores are not equal across generations of machines. So we were actually hitting scaling issues where it wasn't scaling up when it was supposed to. So rather than being at 60% CPU when it was supposed to scale, it was at like 30 or 40% CPU. And we actually started to run out of threads on some of their early clusters, which is a huge problem. And Amazon never really talks about this at all. So I thought I would mention it because you will hit it if you upgrade generations within a cluster. And I'll show actually how you do that calculation. So we started with this fixed number of instances, and we wanted to get to here. We wanted to auto-scale at the container level and at the machine level. Very dynamic environment, fully replaceable. And we probably replace 80% of our machines, I don't know, twice a month. I mean, early on, I was replacing entire clusters 4 or 5 times a day just to stress test it, and it worked pretty well. So we actually wanted to start using all sizes of machines available to us from Amazon. So we're using the compute ones, the C5s. We also want to bring in the memory-intensive ones, so the M5s, because some of our applications needed more memory, some of them required more CPU, so we wanted to get all those options. And we also wanted to bring in the bidding market with the Spot and get up to 90% cost reduction to kind of reduce our costs there. Amazon now has options for this. At the time, it wasn't so great. So we ended up going with this third party called Spotinst. Highly recommend them even today. It gave us a lot of different features. So we were able to mix the machine sizes and families. We were able to use all of our RIs, which we had purchased up front. So any there we don't use is kind of a waste of money. They also have a lot of machine learning algorithms that actually predict when machines are going to shut down within a 15-minute window rather than 2 minutes, which is what Amazon gave us. And what's really neat to me is that they actually fit the capacity of the VMs to the service themselves. So it's kind of like a reverse bin packing. And they also gave us these AZ capacity heat maps. So I don't know if any of you can see this, but on the left-hand side are the different AZs, and then at the bottom are the types and sizes of machines. And you can see that US East 1E basically did not have any of the machine types that we need, so we basically just don't use that. Amazon doesn't provide you with any of this information. I think it's, at least in this format, it's a really great feature. Some other things it does for us, it automatically drains tasks so that you're not throwing 500s or 404s when a task is shutting down. Gives you a little bit of headroom so that if we have a sudden traffic spike, if somebody posts a review on YouTube of Duolingo and suddenly we have 10,000 requests per second more than we were expecting, we have nice capacity headroom there. It also spreads capacity across all the AZs and all the data centers, so that gives you a lot of reliability guarantees in case one of the data centers starts acting a little bit wonky. And the best of the best is that they bill based on how much you save, so they're incentivized to save you money. A lot of actually I'd say almost all of the cloud vendors that say they're going to save you a ton of money, they bill you based on how much you're spending, which is complete opposite, right? Why would you want that? Are you going to save me any money? And it also supported Terraform, which was great. So this is what our auto-scaled environment looks like. These are the different billing options. So reserved is the purple, so that's what we paid up front for. The green is the spot market. So those are the things that can disappear at any moment. So we try to run about 50-50. We don't want to go too crazy. There are some large companies that actually run almost 100% spot. I think that's a little bit too much. And then there's a tiny, tiny sliver of blue, which is on demand. So that's the most expensive. and we barely use any of that anymore. Very quickly, per microservice costs, we try to get services to about 60% CPU and 60-80% of memory usage. That gives you a nice little buffer. Obviously, if your service comes online and the memory usage is going up and to the right, you probably have a memory leak. You should fix it. And another important thing here is you should always have your Docker tasks exit. You shouldn't over-allocate memory, because you might have tasks starting to crash other tasks on the same machine, and you never really want that to happen. I mentioned the adjusting CPU for scaling. This is how you calculate it. You could kind of eyeball it if you want to, but if you have this problem, you should probably screenshot this slide. You essentially multiply the allocated CPU times the current utilization to give you the CPU that you're actually using, and then divide the actual CPU divided by what you actually want in terms of utilization. So there's an example there. I should mention that 1024 units is just one CPU core on whatever machine type that you're using. I think I mentioned most of this. Yeah, that's just in bullet point form. Skip that. Let's just talk briefly about API costs in general on AWS. I think I mentioned this at the beginning, but there are a lot of different hidden costs that are really difficult to track down. So this is our S3 bucket costs a few years ago. So it's an object store. You would think that you'd be paying for actual storage. That would be the thing that you're worried about, but that's not always the case. So it turned out that our bill just kept increasing month over month over month, and our storage was actually going down. I'm like, why are we paying so much more money? So I actually divided the bill into API calls, and you can actually see that list buckets plus get object was over 50% of our costs on S3, which was staggering to me. And it turned out we just had a service that had done their own S3 implementation that was just like going bonkers on S3. Like every single request was like doing a list all my buckets call. So that was actually fairly easy to fix once we found it. There are also lots of gotcha limits on AWS, and I swear I find a new one every couple weeks, even though I've been using the service for 5.5 years. This was a really crazy one. So a little bit of history. EC2, well, still does, runs, what did it used to run on? Oh, it used to run on Zen. On still does, the old instance types. And they switched to a what is it? Yeah, Nitro, but what's it based off of? Yeah, KVM, thank you. So they have this brand new system. A lot of it is implemented in hardware. It's all nice and good. It turns out they stopped caching DNS requests on the machine, the actual physical machine. And didn't really tell anyone. I actually found this in a Reddit post because we had clusters that were throwing these random errors every once in a while. Like they couldn't connect to a different microservice. And we found this DNS request limit of 1024 per second. And if you have a really large machine with hundreds of tasks running on it, you're going to hit this pretty quickly. So we actually just had to put a caching daemon on the machine, which is kind of annoying. I don't know. Yeah, if you're using the cloud, you're going to hit all sorts of crazy limits like this. So just in a summary, we reduced our compute costs by 60% through this project. You can actually see it on the right there from May to October, which also reduced our cost per monthly active user on Duolingo by 30%, and our overall AWS bill went down by 25%. We also had some key results here. So right now we manage about 100 microservices. This is probably around 150, nearing 200 now. This is about a year out of date. All of our teams now deploy their own microservices. Most, I would say 98% of them, deploy and merge, so they don't have to worry about deployment. We now officially support 3 different programming languages, including things like Java and Scala, which were completely new runtimes for us. And we actually hit the quarter after this implementation, we hit 4 nines for the first time ever, which was fantastic. And then again, a 60% reduction in compute costs. So just a quick pitch. If you like this sort of stuff, we're always hiring. Our main office is in Pittsburgh, Pennsylvania. Most of our people are there. But we also have offices in New York City, Beijing, and Seattle. So check it out, or talk to me afterwards. All right, here's the final slide and the one for your phone. So these are all the different tools and services that we use, and there's some really good references there. If you're interested in microservices and how to actually split up your monolith effectively, Building Microservices, Designing Fine-Grained Systems by Sam Newman is kind of the de facto microservices book. Susan Fowler's book is also really good. That actually shows you how to run this stuff in production, which is kind of an operational perspective rather than a developer's perspective. And there are also some really good, quote-unquote, open source references. I find the open guides in GitHub sometimes a lot better than Amazon's own documentation. This is kind of community-driven documentation. They point out a lot of the gotchas that I mentioned actually there. Okay. Quickly, questions?
You're talking about Spotinst. I don't quite understand what that is. Is this something where they essentially like aggregate several different people buying spot instances on Amazon Web Services? Or because he said that they had longer, like a 15-minute window as opposed to a 2-minute window to like whether your spot's going to disappear.
If you're familiar with an auto-scaling group, okay. So what they do, they allow you to scale based on some metric. So we do it based off of memory for our clusters. So if the memory increases, they'll automatically add 1 or more machines to the cluster. And they'll fit it based on the tasks running on that cluster. So we don't have to worry about what size. They'll pick the right size. And they'll also adjust the pricing options to our 50-50 ratio at least as much as possible. So they manage the cluster state for us. Yes.
Same question, or similar about Spotinst. You said it trains ECS tasks. What exactly do you mean by that?
So if you run any sort of application with like a load balancer in front, you might have a period of time where the service still looks healthy, internally, but it really isn't. You might get errors if you hit it, just like you have a startup time before it goes live. So it just makes sure that it's completely drained rather than doing like a kill 9 on the process. So it gives another task some time to start up to replace it. Yeah.
Where do you keep your Terraform code? Do you keep it in one monorepo, or do you split it out per service?
We do both. So we have what we call infrastructure core repo, which is kind of the extreme base level stuff. But all the application level code, so caches, databases, those modules that I showed you live with each service. So the teams can manage their own things. So if we want to add a new feature to like a web service or a worker service, we do it at the module level. We maintain those modules in its own repository. And then on the next deployment, they'll get all the updates. Yeah.
And then what do you guys do with secrets in environmental?
Yeah, we use the KMS service. I actually have an example of this. It's key management service, and it works nicely with Terraform. So here, there's actually a variable for where a secret will go. So that the secret is actually not in the repo. It's out on the KMS service, and it'll be updated whenever we run the Terraform apply. It'll pull the key in. Yeah.
Talking about creating microservices, that was something that was not really tangible.
Mm-hmm.
You guys look at static code analysis, factor that in.
Yes, we do a lot of static code analysis at build time as part of the GitHub review process. So before it's actually reviewed by a human, we go through a bunch of static checks. And also we factor in code coverage and things like that. Yeah.
engineering on call and the grading and your culture I'm wondering about. So an example that popped into my mind is, are there groups that are stuck in bronze and generate the most pages? What are the ramifications of that?
Actually, the one that's probably the most active is the one I'm in, which includes what's left of our monolith, just because it's the largest service. And we're still, it's probably going to take us a few more years at least to finish breaking apart the monolith into microservices. Yeah, we're trying to make a really big effort to smooth out the number of pages across the groups. Yeah. Okay. I think I could do one more. Okay.
So, do you use Duolingo, or are you one of those Rosetta Stone guys?
No, we all use it internally. Yeah.
So can you give it the entire speech in Spanish?
No. Sorry, quickly. Yep.
If you would do this again today, would you look at ECS or Kubernetes?
I'm still all about ECS. I would honestly look at Nomad before Kubernetes.
Even with like EKS available?
Yes, it's not quite there yet, in my opinion. ECS has never gone down. And it's really nice and simple in comparison. It just kind of works. Yeah.
I'm curious if there's any kind of tooling or things on the horizon, pub features that maybe hasn't attained like widespread adoption across infrastructure teams, like in production, that you guys are either thinking about, like what's going to be the new hotness, I guess, or maybe something that's like
Yeah. I'll answer this as quickly as I can. So if you work with containers a lot right now, you'll find that you have like endless sidecars, which drives me insane. I think a lot of that will fold into these different schedulers. I hope. That's my prediction, at least. Yeah. All right, I think that's it. Thank you.